This is a video set of instructions for Ccna 2, Chapter 3, Dynamic Routing. Last chapter we went over static routing, which was basically manually configuring routes into your router. This chapter we're going to discuss dynamic routing, and not really to the extent that it used to be taught in Ccna 2. They've limited it a bit from what the material was before, so let's go ahead and take a look. Excuse me. So what they did take out and have pushed, it looks like, to Ccna 3 is configuring OSPF, which probably would have been the hardest thing we had to do in this chapter. All we have to do is configure RIP version 2, talk about what dynamic routes are and why they're used, how they're used, and take a look at how routing table entries are searched through by your router and how it picks the best one. So this could go pretty quickly. Let's find out. So dynamic routing protocol evolution doesn't show you the prior versions of these protocols, but we had a regular RIP before we had a RIP v2. You can see they've been used since the 80s. I don't think that's a test question. But again, we had regular RIP before RIP v2. We had IGRP. We had just regular OSPF, and ISIS is always ISIS or ISIS. And BGP is for your internet service providers and backbone networks. So that's not something we really work with at all in this chapter or even in CCNA 2. So the ones we would be discussing, the ones to know about by the end of your CCNA are RIP v2, EIGRP, OSPF. Those are the ones we're going to use. ISIS is also more of a protocol that's used by your internet service provider. Okay, I don't want to go too far into detail that you don't need, but I don't think it's discussed anywhere. Well, we discussed what RIP makes decisions on before. It's hop count. EIGRP, that's going to be delay plus bandwidth and a couple other factors that go into it, but delay and bandwidth are the main two. And bandwidth for OSPF. Okay, and that's link state versus distance vector, which we don't have to get into anymore. So, dynamic routing protocol components. Of course, they're used to exchange routing information. They discover remote networks, maintain up-to-date routing information in case anything has changed, a new network has been added, whatever could have happened to alter the network. Choosing the best path to destination networks based on whichever metric that particular protocol uses, whether that's bandwidth or hop count or whatever. Ability to find a new best path if path is no longer available. So that's what dynamic routing protocols will do for you, rather than you having to configure a new path on your own. Main components of dynamic routing protocols, you want to know these by definition, and just the definitions that you see in front of you are fine. You've got data structures, which include your routing tables and databases that your protocols use for its operations. It's kept in RAM, so know exactly what that is, as well as your routing protocol messages, which your routers use to exchange information between devices, keep them up to date, or initially exchange information about routes that your router knows. Okay, so there's a couple different messages they have there. There's hello messages, there's update messages that are sent out there. But this chapter doesn't get into all of that. You've got the algorithm, which is basically what the particular routing protocol uses to determine the best path, whether it's RIP or EIGRP or OSPF. So what does it use? What algorithm does it use to determine the best path? Okay, so you got those here. Again, you want to remember those. Anything else? I don't think so. So we'll go on from there. There's some other terms we could get into, but it's not necessary for the course anymore. So I'm not gonna give you information that you don't need to pass CCNA 2, I suppose, and overload you. So let's stick to what's in the materials. Networks typically use a combination of both static and dynamic routing. We talked about uses for static routes. If you were going to be routing to and from a stub network, you could use a static route. They are handy when you're working with smaller networks, then you don't expect to grow very much, or accessing a single default router. You could use a static route for that as well. So these are some things we saw in the previous chapter about when to use static routing. And I believe this slide is exactly from the previous chapter that shows how you would use a static route to and from R1. Okay, so R1 could use a default static route to get over to these networks over here, because if traffic is not going to either one of these networks, it's always going to the right to R2. So R1 could use a default static route to set that up. And then R2 could use a normal static route to get to the networks on the left-hand side. So no need to use dynamic routing in that situation, even though you could, but you don't have to. And advantages and disadvantages of static routing. I believe we saw this also in the previous chapter. Easy to implement, very secure. Route is always the same, no algorithm, so it's less overhead on the CPU and the RAM. There's resources are not going to be taxed at all, or as much for static routing. Disadvantages, only suitable for simple topologies, and configuration gets a little tricky as you grow the network. Manual intervention required to reroute traffic if a route goes down. Okay, so you've got all of those things that factor in. We already talked about floating static routes, which could assist in a reroute, but we won't get into that again. That was in the previous chapter. And we have dynamic routing advantages and disadvantages. I mentioned last chapter that you want to know the advantages and disadvantages of static. Same thing here. Those are test questions. So your advantages, all topologies where multiple routers are required. Okay, for dynamic, independent of the network size, automatically adapts topology to reroute traffic as possible. So very little user intervention is required if your network changes. The dynamic routing protocol should go ahead and adjust to whatever changes are made to your network and share information about new routes or new networks as they're added. Whereas in static, you'd have to perform all that yourself as the network administrator. Disadvantages can be more complex to implement, less secure because it's sending those routing updates, sending routing information across the network, which potentially could be intercepted. Route depends on your current topology and requires additional CPU, RAM, and link bandwidth, because you are sending out more messages. You're sending out messages about the routes you know. You're sending out hello messages that let other devices in the network know that you're still up and alive, basically. But again, we don't get into that in this chapter, so I'll just stop there with the hello messages and the update messages and move on to the only dynamic routing protocol that we discuss in CCNA 2. So RIP, which isn't really even used that much. So interesting choice, but again, I'm guessing that they have pushed OSPF and EIGRP to CCNA 3 because CCNA 3 and 4 actually were kind of light compared to CCNA 1 and 2. They were quicker courses, only 9 chapters apiece, so a lot lighter than the previous courses, so I'm guessing that's why they pushed it over. Anyhow. So you got router RIP configuration mode. You're going to enable RIP on your router just by typing in from global config router RIP, and then RIP is up and running. You do have to designate which networks you're going to advertise through RIP. Okay, so this statement down here, this command down here shows you what you would end up advertising if you have an interface that is connected to that network. Okay, so typing in this statement doesn't mean this I'm advertising this network. You actually have to type this statement, then have an interface brought up that is connected to that network. So for instance, this 192.168.10 matches this network over here, which is connected to your G00 interface. So since there's a match there, you will advertise that network. Okay. If G00 were not connected to this network, then, well, this network here, the 10 network, would not be advertised. So on the opposite end, you got S000 connected to this 192.168.20 network. So since that's a match also, then this network will be advertised. So this statement alone, or this command alone, does not mean you're advertising this network. You have to have this command and an interface that is connected to the network that is entered with this command. Whoops, don't mean to move that around. Okay, so that's what you have here. You're going to verify RIP. You got show IP protocols, and you'll see that routing protocols RIP, and you've got some other information that will show up down here. Okay, and if you do your show IP route, you can see your RIP entries in the show IP route as well. So that's RIP. That's the old version, actually version 1 that we don't really use as much anymore, excuse me. Version 2 is what we use, and version 2 you activate just by typing in version 2 after you type in router RIP. Okay, type version 2, that's it. Version 2 is activated. What you have to do, or have to be aware of, is that if you're in RIP version 1, RIP version 1 is a class full routing protocol. It doesn't use CIDR notation or subnet masks. Okay, so that's why we don't use it anymore. We don't use class full addresses anymore. But RIP version 1 will send version 1 routing updates, which are class full. But it can receive any. It can receive version 1 or version 2 updates. So if you're in RIP version 1, you can send version 1, receive either version 1 or version 2. If you're in RIP version 2, you send version 2, of course, but you can only receive version 2. Okay, I'm not sure why it's set up that way. That's just the way it works. So version 1 can receive any update, RIP version 1 or version 2. RIP version 2 can only receive version 2 updates. Okay, so just be aware of that. We discussed a little bit about route summarization last chapter, which would be to take networks that are all contiguous or in a row and lump them into one summary route based on changing the CIDR notation or subnet mask. Okay, that is what RIP will do automatically if you don't turn it off. So RIP version 2, that is. RIP version 1 just uses class full addresses, so auto summary is not something that can be disabled. You only do this for RIP version 2. Reason you'd want to is because maybe RIP summarizes your routes into a block that's too big, and maybe you get into a situation where RIP has summarized your route to go off to the left here of R2 and included a network that's off to the right because the summary block was so big that it included a network off to the right. That is going to cause issues in your routing process if you have overlapping networks. Okay, so that's where you turn off route summarization over here. And all you do to make that happen is, so there's no auto summarization of routes, is type in no auto summary from the router prompt, which is this config router prompt right here. So you just type in no auto-summary, and that will turn off automatic summarization. Okay, so you won't see summarized routes anymore. You'll see each route with its own subnet mask and entry in your routing table. Okay, so not something you have to do, but it can cause issues if you leave auto summary on at times. So You need to look at the situation that's being presented to you and decide whether you want to turn it off or leave it on. All right, what else we have? We have configuring passive interfaces here in RIP. So passive interface basically means you don't want to share routing updates through some interface. Okay, so for instance, we have R1 over here. We have R1 or R3, both. Actually, all three routers could use this. So R1 has no routers off to the left. R3 has no routers off to the right. There's no reason to send routing updates in a direction that doesn't have any routers. The switch doesn't care, the host devices don't care about those routing updates. All you're doing is wasting bandwidth, wasting resources, and perhaps providing a security risk if there's some device out here trying to intercept your routing updates to use it for its own evil plans. So you can configure a passive interface that will not send those routing updates. It'll still receive routing updates if they're sent, but it's not going to send them out itself. So in order to do that, you have the command over here. If you're in router RIP, getting yourself into the config router, the config router prompt, you're going to type in passive-interface and then whichever interface you want to make a passive interface. Again, that means you won't send routing updates out that interface, but you could still receive them if they were sent the other direction. So that is configuring your passive interface. Propagate a default route. So if you want to share your default route, okay, which is your gateway of last resort, your default route, we've discussed what that is. Basically, where do I send all traffic that doesn't match anything in my routing table? Okay. If you want to share that with other devices on your network so they don't have to set up a default route, you've already given it to them as R1. So we're in R1 as this example, and that default route has been set up. We did an an IP route 0000000, the default route, yada yada. We've talked about that. So you set up your default route. Okay, then you go into router RIP, and you're going to type in the default information originate command. Default information originate. That is going to allow your router to share that information with R2 and R2 with R3. Okay, so you won't have to set up that default static route on R2 and R3. It will be shared from R1 to those devices. Well, R1 to R2, then R2 to R3. You will go ahead and not have to configure that default static route on these devices because R1 is sharing it. Okay, so again, that command is default information originate. And, well, that's about it. Anything else? I don't think so. So, yeah, R1's the only one that can reach the internet, so they'd all have the same default or gateway of last resort, which would be accessed through R1. Alrighty, and away we go. Believe it or not, we're going to be done before you know it. So, the routing table that is kept inside of your router. How it works, what does it do? So, routing table entries, we've discussed quite a few that you could see in there, directly connected versus OSPF, EIGRP, RIP. How does your router look through the routing table? Okay, here's a example of your routing table. We've got a few different entries in there. Static or default static route, directly connected, RIP. We've seen this before for your directly connected routes. Which network are you directly connected to? And which link or interface is connected to that network and its IP address. Remote network entries, we've got a couple of different letters could come up here. We've got RIP in this instance, okay, with the destination network. Administrative distance of 120, which is the default value for RIP, okay. 2, we know that RIP uses hop count as its metric, so that means that this network is 2 hops away. Our next hop IP, route timestamp, how long we've known about it, and the outgoing interface. routes. Routes are discussed in terms of ultimate route, level 1 route, parent route, child routes. Okay, what does that all mean? So, ultimate route. Your ultimate route has a way off the device, whether that's a next hop or a interface to exit. Okay, so you've got ultimate routes here. There's an interface. You've got an ultimate route for most of these entries. In fact, the only thing you're going to see that isn't an ultimate route is a parent route. So everything that is left aligned most, not indented in, those are all level 1 routes. Okay, level 1 routes. A parent route is a route that has been subnetted. Okay, it's a network that's been subnetted. And you won't see a way off the device like a next hop IP or a interface ID on those parent routes. So for instance, the 172.16.0.0, you see it's got 5 subnets, 3 masks, and there's no next hop, there's no interface ID. You're just seeing, okay, the subnets that are created from that original network. Okay, that is a parent route, and these underneath it that are indented in are, whoops, are child routes. I don't mean to move that. Okay, same thing over here. We got the 209.165.200.0 network. Okay, it's got 5 subnets. This is the parent route, the 209.165.200.0. These are the child routes. Okay, so you've got that. What else? What else? So parent route, these are all level 1 routes again. And an ultimate route, everything but a parent route, here's an ultimate route. They all have a way off of the device. They either have a next hop IP address or a exit interface, or both. Okay, so that's what an ultimate route is versus a level 1 route versus a parent route. So we'll go down and you'll see ultimate routes. We just discussed what they are. Again, you can see that everything here that isn't a parent route is a ultimate route. Just because this guy is all the way to the left in our indent doesn't mean it's a parent. Okay, you see that there's no routes underneath it. It doesn't say that this route has been subnetted at all. It's just a level 1 route. So that's the difference between a level 1 route, this guy here, and a parent route like the one right underneath it. Okay, the parent route has child routes underneath. Okay. So sources of level 1 routes, you've got a network, a supernet, which is basically a summary route that contains multiple networks in it. Okay, you could have those entries, summary networks, or summary routes I should say, and you've got your default route. Okay. And we've got our parent route. Okay, we talked about that and how there's child routes underneath. Okay, these ones aren't indented in at all, but you can see those entries there. Oh, they are indented in. It's just that the next line is coming all the way over to the left. So you can see the indent there. Parent route here as well. And highlighting the child routes for you. Okay. So you've got level 1, level 2 child, ultimate, parent, routes. Okay. How does the router look for the best route through your routing table? So let's take a look at that next. So your lookup process. Number 1, your router is going to look for a best match as a level 1 ultimate route. So best match, I think they're going to get to it, but basically a best match has the most matching bits. Okay, so if you're 172.16.1, if you've got that rather than a 172.16.0.0, it's going to take the 1 if the 1 is matching the network that you're trying to get to. Even if the administrative distance for a certain route is lower, if the bits match, if more bits match, the router is going to take that entry, regardless of administrative distance. You'll see that again in a couple slides. Okay, so I'll restate that. So if your best match is a level 1 ultimate route, that one's used. That means it's level 1, all the way aligned to the left. Let's see, we don't have one there. But an entry like this RIP protocol would be an ultimate route. It's level 1, it has an exit interface, it has a next hop, so that would be used first if there's a match for that type of entry. If there's not a match for that, it's going to look at your level 1 parent routes and see if there's a match there. Okay, and if there's a match in the level 1 parent route, okay, the best match is the level 1 parent route, then it's going to look in its child routes to see if there's a match there as well. Okay, so that's what you'll see on the slide. We'll proceed to the next step. It examines the child routes of the parent route for a best match. Okay, if there is a match within that child route, has the match. Okay, that subnet is used to forward the packet. But if there's no match from the child route, it proceeds to the next step. So that would be like, let's see here. If I have this 172.16.0.0 network, all right, this goes all the way from 10 through 40. Okay, let's say that the network I'm trying to reach is 50. Well, it's not down here. Okay, it's not down there. So if it doesn't match that, it's not going to use, well, any of these routes because there's no interface or next hop associated with 50. All right, so it's possible that you look through a parent route and you don't find a match. If you do find a match, though, it's just going to go ahead and send it out whichever interface that it needs to, or to the next hop IP address. Okay. The router continues searching level 1 supernet routes. So now you're looking for supernet routes, summary routes that might match that entry. Okay, including the default route if there is one. Now, if you do have a default route, I mean, it's going to match that at the end pretty much no matter what. So you'll have your traffic forwarded out the default route if all else fails. But if if it does match a supernet or default route, it'll use the supernet first. If it doesn't match a supernet, it'll use the default route and forward the packet. If there's no match in the routing table at all, there's no default route, then it's just going to drop the packet. Okay, we've discussed that if there's no match in your routing table, that packet will be dropped, which is why we typically type in or configure a default static route. So the best route equals the longest match. If you have some destination IP, your route that matches the most bits will be used regardless of administrative distance. Okay, so remember that. We've talked about administrative distance a lot. If there were two matches of the exact same length, then administrative distance would come into play. But if you've got more bits in one route than another, it's going to be used regardless of administrative distance. Routing tables in IPv6, a little bit different because you don't have subnet masks or anything. So since you don't have subnet masks, there are no parent and child routes. Basically everything in an IPv6 routing table is an ultimate route, because every entry has an exit interface or a next hop IP, one or the other. So everything in IPv6 is an ultimate route with a path off the network. Okay, there's the IPv6 routing table entry broken down, and well, that's it. Okay, so this is actually a pretty light chapter. Static routing may improve a little tougher than this. I don't know. They took out OSPF and EIGRP, so, well, EIGRP wasn't in there in the previous material, but OSPF was. Anyhow, that's it for Chapter 3 on dynamic routing. We'll probably do this over spring break. We'll see. But we'll continue to discuss the labs in class.